Hello, this is Sadbir. The topic of our discussion in this video is null space of a matrix. The null space of the matrix is defined as the collection of all the solution of this linear system Ax is equal to 0. That is when the right hand side vector is a 0 vector. For example, if you have a matrix A, which is a 2 by 2 matrix, 1, 2, 3, 4. The null space of this matrix, you would like to calculate all the solution, which when you multiply basically to this matrix, it produces the 0 vector. As you can see that the one obvious solution to this system is 0, 0. So if I place 0 here and 0 here, and I multiply this vector to this matrix, I will get the 0, 0 vector. So this is the one element which is in the null space. In fact, in this case, this is the only element in the null space of A, which we will see later in this video, why this is the only element. Now, another example is if I take again 2 by 2 matrix, this time I will take 1, 2, 2, 4. And now I'm asking the null space is basically all the possible vector which I have multiplied to this matrix 2, 4, which produce the 0 vector. And to compute the null space of this matrix, the one obvious solution is of course 0, 0. And you can see also if I multiply if I place 2 here and 1 here, that will also produce the 0, 0 column. So this is a one solution. So this is also an element in the null space. In fact, 2, negative 1 is also in the null space. And also 4, negative 2 is in the null space. And negative 4 and 2 is in the null space, and so on. And you can see that in this case, there are infinite number of elements in the null space of a matrix. Now, let me give you some few more information about the null space of a matrix. If a matrix A is of order n by m, then the null space of the matrix, which is denoted by n of A, is a subspace. Is a subspace of r to the power m. And also one more remark, if A is invertible, if A is n by n matrix and is invertible, you can see that if A is invertible, then there exists A inverse when you multiply by A, that gives you the identity matrix. This is the definition of invertibility. So if I multiply to this equation, which is my equation of the null space, on both sides A inverse, I will get this A inverse turn to identity matrix multiplied to the column vector X is gonna produce X is equal to 0. So this is interesting observation. If the matrix is invertible, the null space of the matrix is only contain 0 vector, which you can see in the case of our first example, which we consider here. This matrix was invertible. That was the reason the null space of that matrix is only contained the 0, 0 vector. If the matrix is not invertible, then its null space must contain at least one non-zero vector, which you can see here. It has many non-zero vector, but at least more than one, because this matrix was not invertible. Here I have one quiz problem for you to practice. please pause the video for 1 and 2 minutes and answer this problem. Now we are going to study the geometry of the null space. So for the simplicity, I'm gonna take the example of a matrix 2 by 2 and 2 by 3. But the higher order also can be treated in a similar manner. So let's suppose I have matrix 1, 2, 3, 4. And how I can draw the null space of this matrix? So because this is a XY plane, null space is in R2 because there are number 2 column of this space. So 2 by 2 matrix. So if I plot the first column, so I can, let's suppose this is my V and that is my W column. So if I plot V, so 1, 3, this is a column V, and 2 and 4, so 2 and 4 is going to be somewhere here. So now what is a null space? A null space is that what vector you multiply, basically what linear combination you take of this vector and that vector, which produce the zero vector, which produce this vector, which is the 0, which has no length. So it means what alpha you should choose, you multiply that to v vector, so alpha v vector, and then you multiply some beta to w vector, and then you add them, and then you get a 0 vector, because this is what it means by when we say ax is equal to 0, means for what values of x this linear combination is 0, or this combination is producing this vector. So as you can see that if I choose my alpha and beta non-zero, I will not be able to draw any parallelogram of these vector that will be a 0 vector. So the only possible solution in this case is if I take alpha is equal to 0 and beta is equal to 0, and then I draw the diagonals. Because in that way, this vector is going to approach to 0, and that larger vector is also going to approach to 0, and you're going to have a trivial diagonal, which is going to be a 0, 0 vector. So in this case, we can say that the null space of this matrix is just 0, 0 vector. So as you can see that if the column of the matrix is not parallel to each other, then the matrix is a 2 by 2 matrix, then the null space of that matrix is going to be 0. Now let's look at another example. In this case, I'm gonna take the example of matrix 1, 2, 2, 4. And we will draw the picture of the column space or the column of the matrix. So 1, 2 is here, and basically 2, 4 is vector is here. So now if this is my vector v and this is a vector my w, I would like to rescale this vector v by some alpha and the vector w by some beta, so that when I add them, it produces a 0 vector. So in order to do that, I must take some beta, or so there's one way to do is, if I multiply alpha, basically -2, it will produce this will be a -2 v vector, and I just take beta is equal to 1, and that will basically the exactly same vector here if I take beta is equal to 1 w. And now if I add them, I will get a 0 vector, because this vector is in the direction, in the positive direction. This one is the same length in the negative direction. So if you take the parallelogram, the trivial parallelogram is going to have the diagonal, which is a 0. So you can see that the null space of this matrix is gonna be containing at least -2 and then 1 vector. 0, 0 is always there, because if you take 0, you can basically every vector collapse to the 0 position, and then you're going to have a trivial diagonals, and which is going to be at the 0, 0. So as you can see, there will be many other vector, but they will be all scalar multiple of this -2 and 1 vector. So all the scalar multiple of this will be in the null space. Because if you take alpha little bigger, you can adjust beta accordingly. When you add them, you get the 0 vector. So I'm going to take one more example. Let's say A is equal to 1, 0, 0, 1, and then it is 1, -1, -1. So if I draw the picture of the null space of this, it's gonna be look like this. So you have a vector 1, 1 here. So this is a vector 1, 1, 1, 0. Let's suppose this is a vector 0, 1, and definitely the vector 1, 1 is here. So as you can see, if I take the linear combination of this vector, and this vector, I would like to produce the 0 vector, which has in the origin with no length. So one way to do is if I just multiply this by 1, so I just take 1 here and 1 here, and I draw the parallelogram. So you can see that if I plot the parallelogram, the diagonal of the parallelogram is going to be aligned with this vector, but in the opposite direction of this vector. It's going to be the opposite direction of this vector. So now if I add these two vectors, I'm going to produce the 0 vector in the middle. So I can say that my the null space in this is going to be one of this, and one of this. So 1, 1, 1. So this is my null space of this 2 by 3. And I can see all the multiples. It's not just one vector. If I take any multiple of that, so all the multiple of this vector will be in the null space. Of course, 0, 0 vector is the multiple of 1, 1, 1. So 0 vector is also in the null space. You can also consider the higher examples, but it will be a bit harder to view the geometry of the another systems. But in the next video, we will compute the null space of the matrix more mathematically. Here I have one more quiz problem for you to practice. Please pause the video for 1 and 2 minutes and work on this problem. Now, how we can use the null space to calculate the solution of this system, of our linear system AV is equal to B. So we know that if B is in the column space, so the first thing we need to verify is if B is in the column space of A. Because if the B is not in the column space of A, this system is not solvable. So if B is in the column space of A, then AV is equal to B is solvable, that we can find a solution. So let's suppose first B is in the column space of A. Then if I write the solution V as the solution in the null space and a particular solution VP. So what I'm going to do is I'm going to find all the solution which is in the null space, and I'm going to find one solution which is not in the null space of the matrix. So then you can see that if I plug that here, so A Vn plus Vp is equal to B. And then the multiplication is distributed. So I'm going to distribute. So An is equal to Vp is equal to B. But since An is in the null space of the matrix, so this will be a 0. So then AVP is equal to B. So in order to solve the system, so we need to find two things. One is we need to find the particular solution of this system. We need only one solution of this linear system. Then we can generate all the solution by taking the null space and adding that one particular solution, which will be the topic of our next discussion, that how to find the complete solution of the linear system when the B is in the column space of A. So what we will do, we will find the null space of the matrix, and then we are going to add one particular solution in that, and that will give us the complete solution of our linear system. Okay, this is the end of this video. I will see you in the next video. Bye for now.